Hello everyone, my dear students, dear friends and colleagues. Now in this video lecture, in today's video, we'll discuss something new. In the previous video lectures, we have discussed physical chemistry, we have discussed inorganic chemistry. Now after discussing all this, we are left with organic chemistry. So today, after this video lecture, we will discuss organic chemistry. So we are all aware of the term organic chemistry. So basically, in the simplest or easiest way, chemistry which deals with the properties, extensively discussing about the properties of carbon and its compounds, excepting for few compounds like carbon monoxide, carbon dioxide, carbonates, bicarbonates. Rest of the elements, rest of the compounds or molecules of carbon are classified as organic. Now we are going to discuss different types of organic compounds, their methods of preparation, their properties, physical as well as chemical properties. So starting with this organic chemistry, in the 11th class, we have discussed the basics of organic chemistry, and after that we have discussed hydrocarbons, that is alkanes, alkenes and alkynes. Now in continuing with those, we will start with halogen substituted hydrocarbons, which are collectively known as haloalkanes or alkyl halides. That means one of the hydrogen of alkane is being replaced by halogen, and this becomes halogen substituted alkanes, alkenes or alkynes. These are known as haloalkanes, haloalkenes, haloarenes if hydrogen of benzene is replaced by halogen. So starting with this, haloalkanes So today's heading will be haloalkanes. So definition is halogen substituted alkanes, which are also known as alkyl halides. Halogen substituted alkanes are also known as alkyl halides or known as haloalkanes. So as I told you, we may have alkane, alkene, alkyne. So if you look at this, suppose take this may be alkyl group, this may be alkyl group, this may be alkyl group, this may be allyl group, this may be aryl group. If this hydrogen is replaced by halogen, then this gives you Rx. So this compound Rx, this is what we call as halogen substituted alkanes or alkyl halides or haloalkanes. What this X may be chlorine, bromine, fluorine or iodine, any of this halogen. So this is haloalkanes or alkyl halides or halogen substituted alkanes, alkenes or alkynes. Now these may be of different types, as I told you. Look at this. We have, suppose look at this, CH3, CH2X. So if you look at this, this carbon is sp3 hybridized. So this group is known as alkyl group. So this is alkyl halide. Look at this, CH2 double bond CHX. Now halogen is attached to sp2 hybridized carbon. So we have a carbon, this carbon is sp2 hybridized. Look at this, we have a double bond here. So if halogen is attached to sp2 hybridized carbon, these type of alkyl halides, these types of halides are known as vinyl halides. So in organic chemistry, this particular group, this group is known as vinyl group. So if halogen is attached to vinylic carbon, this is known as vinylic carbon, this is known as vinyl halides. Look at this. Now halogen is bonded to an sp3 hybridized carbon. This carbon is sp3 hybridized, and carbon next to sp3 is sp2. So we have this type of group. If halogen is attached to these types of group, this is known as allyl halide. In organic chemistry, this particular group CH2 double bond CH CH2, this group is known as allyl group. So halogen attached to allylic carbon, this is known as allyl halide. If halogen is attached to aryl group, that is benzene or benzene related compound, this is known as aryl halide. Or we may also have look at this. If suppose we have this group, if two halogens are bonded to same carbon atom, look at this, this is carbon, and in this carbon two halogens are present. If two halogens are present on the same carbon atom, then we say this is geminal dihalides, geminal compound. So geminal, or simply we say gem, is a particular is a word which is used for specific those types of compounds in which the same carbon bears two identical groups. If the functional group, two functional group is present, means two identical functional groups are present on the same carbon atom, then this is known as gem. This is for all functional groups. If we have two OH, then also known as geminal alcohol. If we have NH2, then also known as geminal amines. So geminal is for those compounds in which two identical groups are present on the same carbon atom. We may also have this type of, look at this, RCX, CHX. These are two alkyl groups. This may be same or this may be different. But look at this, halogens are present on adjacent carbon atom. If halogens are present on adjacent, we have two halogens attached to two different carbon atoms, but these carbon atoms are adjacent carbon atoms. So if two halogens are bonded to two carbon atoms, then this is known as if vicinal. This is known as vicinal dihalides or simply VIC. So if two halogens are on the same carbon atom, we say this is geminal dihalide, gem compound. If these are present on adjacent carbon atom, then this is known as vicinal. So this is the types of halogen attached to types of carbon atom. Different types of carbon with different types of halogen होने से we get specific names. Or some of the compounds may contain allylic भी vinylic भी present हो सकते हैं. तो take this compound. So we have CH2X and X. So look at this. This group is similar to this group. So this is vinylic part. So again look at this part of the molecule. Look at this part of the molecule. This part of the molecule is similar to this allylic group. So we have CH2, C double bond C, CH2, C double bond C. So this part is what we call as allylic. So both allylic and vinylic may be present in the same compound. So if you look at this carbon is sp3, then this is also known as alkyl halide. So these are different words, different names given to different types of alkyl halides. Now, these alkyl halides means monohalogen substituted alkanes may be classified as primary, secondary, tertiary. Now let's have a look at this classification of monohalo compounds. Let's have a look at the classification. Classification. CH3X primary, secondary and tertiary. So these monohalogen substituted alkanes or simply alkyl halides are classified as methyl halide, primary alkyl halide, secondary alkyl halide and tertiary alkyl halide. Now this is known as methyl. Now in some of the books or some of the authors consider this methyl halide as primary, but if you look at this definition of primary very closely, so the word primary is used for those compounds in which the reference carbon is attached to only one carbon atom, then we say this is primary. So look at this. We have, look at this, R CH2X. So if you look at this carbon is your reference because we are talking of this halogen. So carbon bearing halogen is attached to only one carbon. So if the carbon bearing halogen is attached to only one carbon atom, we say this carbon is primary carbon, and if halogen is attached to primary carbon, then this is known as primary alkyl halide. So look at this, in this case look at this, there is no carbon, so only we hydrogen, so I place this as a different group, that is methyl halide. So primary means the reference carbon should be attached to only one carbon atom, that is primary. Now coming to secondary, we have RCH So look at this, we are talking of this carbon atom bearing or in which halogen is bonded. So this carbon in which halogen is bonded is attached to two other carbon atoms. So those carbon atom which is bonded to two other carbon atom, this carbon is known as secondary carbon, and halogen is attached to secondary carbon. So we say this is secondary alkyl halide. If the carbon bearing halogen is bonded to three other carbon atoms, R is your alkyl group. This is halogen. Now look at this. This carbon is our reference carbon. This carbon is my reference carbon because this is the carbon in which halogen is bonded. So look at this. This carbon bearing halogen is bonded to three other carbon atoms. So this carbon atom is known as tertiary carbon. So if halogen is attached to tertiary carbon, we say this is tertiary alkyl halide. So this is just classification of alkyl halide based on the nature of carbon in which the halogen is bonded or present. So these carbon may be simply methyl, this may be primary carbon, this may be secondary carbon, or this may be tertiary carbon. So look at this example. So we have this example. To look at this, let's classify. This carbon having halogen is attached to how many carbon? 1, 2, 3. So carbon bonded to 3 carbon atom, this is tertiary carbon. So this halogen is defined as tertiary halide. If you look at this carbon in which halogen is bonded to two other carbon atoms. So this carbon becomes secondary and this is classified as secondary halide. And look at this, the carbon bearing halogen, this is the carbon having halogen, this carbon is bonded to only one carbon atom. So this is classified as primary. So this classification is very simply based on the number of carbon atoms to which the reference carbon is bonded. We can classify into primary, secondary, tertiary, etc. etc. So this is the classification of alkyl halides. Now coming to the nomenclature part of this alkyl halide, though we have discussed the nomenclature in detail in 11th class, but still let me give you a brief idea about this nomenclature of this alkyl halides. Means naming of alkyl halides. Suppose look at this. This compound, because one of the hydrogen of methane is replaced by chlorine. So this is a substituent. So substituent is named first followed by name of the parent hydrocarbon. So parent carbon is 1, that is meth. One of the hydrogen is replaced by halogen. This halogen is chlorine. So this nomenclature, this is chloromethane. This is substituent. This is root word meth. And this is primary suffix which indicates that this is a saturated compound. Take this CH2 Cl CH2 I. If you look at this, one is chlorine, the other one is iodine. Both are on two different carbon atoms. This is one carbon, this is two carbon. Now the question is how to locate the position. In such type of case, we'll follow the alphabetical order. So look at, this is chlorine C, this is iodine I. So these carbon should be named as 1, this carbon is named as 2. So look at this, 1 chloro dash 2 iodo, number of carbon atom is 2, that is 8, primary suffix is ethane, ethane means 1 chloro 2 iodo ethane. Similarly, look at this, CH3, CH3, take this I, CH2, CHI, CH2, CH3. Now we have iodine, methane as a substituent in different position. Now in such type of case, we'll take the help of lowest locant rule. That means the sum of the locations of the substituents should be the lowest possible. So look at this, we have two possible naming, counting. Counting from this side, 1, 2, 3, 4, 5, 6. We can also start numbering from this side, 1, 2, 3, 4, 5, 6. From this side, substituents are at position 2 and 4. So we have 2 plus 2 plus 4. So this comes out to be 8. This is summation of the locations of the substituents. We have 2 methyl, 2 iodine and 4 iodine. Coming from this side, the position of substituents are at carbon number 3. So we have 3 plus, we have substituent at part 5. So 5 plus 5. So this comes out to be 13. Now look at this. Lowest sum rule says out of the possible ways, the numbering should be done in such a way that lowest locant sum rule is followed. So 8 is less than 13. So this numbering is not allowed. So look at this. We have these substituents. We have to name the substituents. This is methyl, M. This is I. So I comes before methyl. So we have to name this I first. To look at this. This is 2, 4 di iodo 2 methyl, number of carbon atom is 6, hex, primary suffix is A and E, hexane. So 2,4-diiodo 2-methyl-hexane is the name of this compound. Similarly, I'll take one more example here. It is CH3, CH2Cl. Now we have this. Now ring carbon contains 5, so these carbons ring should be considered as a parent because side chain contains one carbon, so the number of carbon in the ring is more, so ring is to be considered as the parent chain. Now in this we have to identify the locations. So this carbon is named as carbon number 1, 2, 3, 4, 5. Now why I am taking this, we'll see the reason. If I take this numbering, to number of substituent is 1 plus 1 plus 2, that is 4. But if I start numbering, this is from this side. If I start numbering in opposite direction, in this way, this is 1, this is 2, 3, 4, 5. Then the substituents are 8, carbon number 1 plus 2 plus 2. So this becomes 5. So again, lowest rule says this numbering is not allowed. This is the allowed numbering for this hydrocarbon chain. So starting with this, look at this. At carbon number 2 we have methyl. 2 chloromethyl 1 dimethyl cyclopentane. So this is how we name halogen substituted alkanes. So simply saying, we have to follow standard nomenclature. First we have to set the longest carbon chain, then we have to number the chain. Numbering should be done in such a way that lowest possible value or lowest locane is given to the substituents. If two or more than two possible ways of numbering are formed, then lowest sum rule should be followed. So this is a brief idea about the naming of halogen substituted alkanes. After this, we will come to the general methods of preparation of monohalogen substituted or dihalogen substituted या polyhalogen substituted alkanes. So coming to general methods of preparation. General methods of preparation. तो first of all हम लोग चलते हैं from alcohols. How to prepare alkyl halides from alcohols? So under this alcohol we have different types of methods. So the first method from alcohol, that is by reaction with HX. A reaction with H is hydrohalic acid. So we have look at this ROH. R is alkyl group, OH this is alcohol. Now this alcohol may be primary, may be secondary, or may be tertiary alcohol. These alcohols react with HX hydrohalic acid in presence of catalyst ZnCl2 H2SO4. When this gives you Rx plus H2O, this group ZnCl2 and H2SO4, this is acting as a dehydrating agent. Dehydrating agent means an agent which helps in the removal of water molecule. So this is the first method of preparation of alkyl halide from alcohols. Now in this method, some few important points that we have to keep in mind while writing a reaction is, the points to be kept in mind is, the reactivity order of HX. We have different types of hydrohalic acids. Then what is the reactivity order of hydrohalic acid? HI is the most reactive, followed by HBr, followed by HCl, followed by HF. So hydroiodic acid is the most reactive and hydrofluoric acid is the least reactive. So this is simply based on the acidic strength. So the more is the acidic strength of HX, more will be the reactivity for this reaction. So HI is the strongest acid, HF is the weakest acid. So the fastest reaction with HI, that is reactivity order of HX. Reactivity order of alcohol. For this reaction, the most reactive alcohol is the tertiary alcohol is the most reactive, followed by secondary, followed by primary, followed by methyl alcohols. So the fastest or the maximum yield of alkyl halide will be formed if we react with tertiary alcohol with HI. Then the maximum yield will be formed. So second thing, next thing, this reaction occurs through carbocation formation, occurs through carbocation intermediate, formation of carbocation intermediate. Now let me give you some specific examples. Take this RCH2CH2OH. Suppose we have this. This reacts with HCl hydrochloric acid in presence of ZnCl2. I am taking anhydrous. When this gives you RCH2 CH2Cl plus H2O. Now in this reaction, if HCl plus ZnCl2, this is taken as 1:1 ratio, then this mixture is known as Lucas reagent, and the reaction with test is known as Lucas test. So just keep in mind, Lucas reagent is 1:1 mixture of HCl and ZnCl2. Now this being primary, this helps in easy removal of this OH, and this ZnCl2 is acting as a catalyst, Lewis acid catalyst. Similarly, we can also take RCH2OH reacts with HBr. Now react with sulfuric acid in presence of sulfuric acid. When this gives you RCH2Dr plus H2O. We can also calculate this RCH2OH reacts with HI. Even at room temperature, this reacts to give you RCH2I plus H2O. So all alkyl halides except this HF, we can prepare alkyl chloride, alkyl bromide and alkyl iodide. So as I told you, this is a reactivity order, and what is the intermediate that is formed in this reaction? That is carbocation intermediate. Now the question is, whenever carbocation is formed as an intermediate, most likely there may be some abnormal product. This abnormality is due to the rearrangement of the carbocation, because carbocation has got a tendency to undergo rearrangement from a less stable to a more stable carbocation. So I'll give you the mechanism of this reaction. Mechanism of this reaction. So I'm giving these steps. These are OH, that is alcohol. Now this alcohol reacts with H plus ion. Now this H plus ion is coming from HX. So HX being an acid, ion has to give you H plus ion, and this H plus ion is acting as a catalyst. So now look at this, we have this oxygen. Oxygen is having 2 lone pairs of electrons. So this oxygen is a basic site. So acid reacts with base to give you protonated alcohol. The first one is acid-base reaction. In the second step, these ROOH reacts with halogen minus halide. If this group is primary, if the group are alkyl group is primary, then this reacts in this way. Look at this. These X minus attacks from the rear side, and this RO bond cleaves and oxygen is electron is taken up by oxygen, and this gives you RX plus H2O. This is the product form. But if the alkyl group happens to be secondary and tertiary, this is, or these are, if these are is secondary or tertiary, then look at this. These RO bond breaks, electron is taken up by oxygen, and these forms R plus, that is carbocation intermediate. So carbocation stability says tertiary carbocation is the most stable and methyl is the least stable. So stability order says tertiary, secondary, primary and methyl. Now since tertiary carbocation is the most stable, so this cation formation will be most likely or easiest way can be prepared from tertiary alcohol, and that was the reason why tertiary alcohol was the most reactive. So after this, look at this. This has two possibilities. These carbocation may undergo a rearrangement to a more stable carbocation, or this may simply react with X minus to give you RX. This is the product. After this rearrangement, a more stable cation will be formed, and that cation again will combine with X minus ion to give you RX. So this is the steps of mechanism. So based on these steps, let me give you some examples of rearrangement. Take this CH3, CH2, OH. This reacts with HI. This is primary, so there is no question of rearrangement. So this gives you CH3, CH2I. Now take this CH3, CH3, CH2OH. Now this reacts with HI, and the product form, look at this, I am giving this star mark. The product form is CH3, CHI, CH3, CH3. If you look at it, this is totally unexpected product. Oxygen OH was on this CH2 group. Now I minus should have been at this carbon, but this is attached to this carbon. So there is change in carbon skeleton. So if you look at this mechanism, look at this. We have CH3, CH, CH3, CH2, OH. This reacts with H plus ion, when this gives you CH3, CH, CH3, CH2. So I am combining these two steps. Force this reacts to give you protonated alcohol. Now protonated alcohol breaks this water molecule, and this gives you cation. Now these cation can undergo rearrangement. Look at this. CH3, CH, CH3, CH2 plus. This is primary. Now look at it. This primary can rearrange to a more stable tertiary by this hydride shift. This hydrogen minus shifts from this carbon to this. That is H minus shift, hydride shift. By this hydride shift, we get this carbocation, because hydrogen is leaving with this electron and hydrogen negative is attached to this carbon, so this becomes CH3 and this carbon is devoid of 1 electrons. So look at this, primary is converted into a very stable tertiary carbon cation, and finally this tertiary CH3, C positive, CH3, CH3, these combines with I minus, so this is electrophile, this is nucleophile. When this gives you CH3, Ci, CH3, CH3, so this is the product that is formed. So here we have rearrangement of carbocation. So whenever there is a possibility of rearrangement, carbocation will try to rearrange to a more stable cation. After this, the final product will be formed. I'll give you one more example of rearrangement. Take this CH3, CH3 here, CH3, CH2, OH. This reacts with HI when this gives you CH3, H3, Ci, CH2, CH3. This is, again, look at this, there is change in carbon skeleton. So there is some unexpected product formed. So whenever formation of unexpected product is there or abnormal product, the reaction may be through carbocation, and carbocation has a tendency to undergo rearrangement. So looking at the mechanism, look at these steps. We have this CH3, 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 CH2, OH reacts with H plus ion when this gives you this cation. So if you look at it, this is primary, so which is very unstable. So immediately in the second step, this will undergo rearrangement. So in the previous case, there was hydrogen. By this hydrogen shift, we get tertiary. But since there is no hydrogen, then this alkyl group has to undergo shift, that is methyl shift. These undergo shifting here, CH3 minus shifting. So by this methyl shift, we get this CH3, CH3 positive, CH2 and CH3. So we have, look at this, by this methyl shift, we get a very stable tertiary, and finally this tertiary cation combines with I minus, which is present here. So this gives you CH3, CH3, Ci, CH2, this is 3. So this is how we obtain a rearranged product. So ये तभी मिलेंगे अगर आपके पास ऑप्शन है कार्बोकेटाइन रीअरेंज करने का. अगर कार्बोकेटाइन रीअरेंज नहीं कर सकता है तब तो नहीं करेंगे. So this is first method, that is reaction of alcohols with HI. Now second method from alcohol, ये मैंने आपको एग्जांपल दिया. Second method from alcohol, that is by use of PX3 and PX5, phosphorus trihalide or phosphorus pentahalide. So the reaction is, as you look at this, we have this alcohol combines with PX3 phosphorus trihalide when this gives you RCl plus H3PO3. So please focus on this side product, phosphorus acid is formed. So to balance this reaction, 1 mole of PX3 combines with 3 moles of alcohol to give you 3 moles of alkyl halide, and 1 mole of phosphorus acid is formed. Take this. We can also modify this reaction as ROX reacts with halogen in presence of red phosphorus, then also we give the same product. So what is happening is this phosphorus first combines with X2 and this gives you PX3, and finally this PX3 reacts with alcohol to give you this product. So in some of the books you may have alcohol plus PX3, then alkyl halide plus phosphorus, or this may be modified as alcohol plus H2 plus the red phosphorus. So X2 plus red phosphorus first gives you trihalide, and this trihalide further reacts with alcohol to give you alkyl halide. Or we look at this ROH plus PX5. So phosphorus trichloride, pentachloride or pentafluoride. Bromide and iodide is less stable. So this gives you RX plus POX3 plus XX. So look at this, there is a difference in side product. With PX3, phosphorus acid is formed. With PX5, phosphorus oxyhalide is formed. So 1 mole of alcohol reacts with 1 mole of PX5 to give you 1 mole of alkyl halide, 1 mole of POX3 and XX. So this is the reaction. Now for this reaction, what you have to keep in mind is this reaction reactivity order of alcohol is primary alcohol is the most reactive, followed by secondary, followed by tertiary. If I say primary is the most reactive, means maximum yield of alkyl halide will be obtained if I start with primary alcohol. With tertiary alcohol, there is chances for dehydration leading to the formation of alkene. So we are not focusing on alkene, we are focusing on formation of alkyl halide as a major product. For this, we have to take this alcohol to be primary. Second thing, this reaction does not involve formation of carbocation. In this reaction, there is no formation of carbocation. Since there is no formation of carbocation, no rearranged or abnormal product will be formed. No rearranged or abnormal product is formed. So this thing you have to keep in mind for these types of reactions. So I'll give you some specific examples. So look at this, we have CH3, CH2, OH reacts with PI3. So this gives you CH3, CH2I plus H3PO3. This reacts with PCl3, so this will give you chloro compound. If this reacts with PBr3, this gives you CH3, CH2, Br, etc. Side product is same, H3PO3. Take this reacts with PCl5, when this gives you CH3, CH2, Cl plus POCl3 plus HCl. This is PCl5, this is PX3. So this is how alcohols can be converted to alkyl halides by reaction with phosphorus halides. So we may take up trihalide, we may take up pentahalide. Next method of preparation of alkyl halide from alcohol is a reaction with to thionyl chloride. Thionyl chloride. Now this method is specific for preparation of chloroalkanes because bromide iodide compound is unstable here. So we have look at this. ROH reacts with SOCl2. This may have presence of pyridine as a solvent or may not have pyridine. I'll give you different reaction based on this presence or absence of solvent. When this gives you RCl plus SO2 plus HCl. Now this method, keep in mind, this method is one of the most convenient or most important method for preparation of alkyl chloride. Most important method for chloride preparation. The reason being, look at this, the byproduct, these sulfur dioxide and HCl, these byproducts are gas. So normally in chemical reaction we have to filter so that we get the purified compound. But in this reaction, alkyl chloride is a liquid. We have sulfur dioxide gas, HCl gas. So this being gas easily escapes from the reaction mixture and not for further purification. So if question says why this method is the most important method for chloride preparation, because the side products sulfur dioxide and HCl are gas and no further purification is required. So this is reaction with thionyl chloride. Now let me give you the mechanism here. So we have looked at this. How to remember this reaction? I'll give you just. We have this ROH, then we have looked at SOCl, Cl. So RCl, SOO, sulfur dioxide, HCl. So we have this. Now look at this. Coming to the mechanism point or the mechanism part of this reaction, because again we have to discuss this mechanism in alcohol also. Let me discuss here again. So we have looked at this ROH. This oxygen is having two lone pairs of electrons, so this is acting as a nucleophile. This reacts with sulfur, Cl, sulfur, double bond O, Cl. This is acting as a nucleophile, this acting as an electrophile. So this nucleophile attacking electrophilic sulfur. When this RO H positive sulfur O minus Cl. So this is nucleophile attacking electrophile. Now this electron is coming back to sulfur and this Cl is moving out from this sulfur, and simultaneously this electron sharing between oxygen and hydrogen is transferred to oxygen. So we are removing HCl, H plus and Cl minus is removed. So we have minus HCl and this gives you RO S double bond O Cl, alkyl chlorosulfide. So this is one of the intermediate that is formed in this reaction. We'll focus on this intermediate. So we have first step. Second step, reaction may be in presence of pyridine or in absence of pyridine. So firstly, in presence of pyridine. When this reaction is carried out in presence of pyridine, what is happening is, look at it. In the first step, there is removal of HCl. So HCl reacts with pyridine. Pyridine is a base, nitrogen having a lone pair of electrons. So this is acid, this is base, and this reaction gives you pyridinium hydrochloride plus Cl minus. So we have free Cl minus. Now this free Cl minus reacts with this intermediate in this way. Look at this. This Cl minus reacts with RH double bond O. Sorry. And this Cl minus is attacking from the rear side of the leaving group. This is the leaving group and this is attacking group. So attacking group is attacking from the rear side, and this electron is transferred between sulfur oxygen, and this Cl minus leave the system, and this reaction is what we call as SN2. Just for the time being, remember this is SN2 reaction, substitution nucleophilic bimolecular reaction, and this gives you RCl, or simply having RCl or ClR plus sulfur dioxide gas is released. And in presence of reaction, Cl minus is attacking the leaving group from the rear side. If this reaction is taking place, the reaction mechanism is known as SN2, and if this carbon R alkyl group is a chiral, then there is a formation of inverted product. Inverted product formation if R is chiral. And if R is attached to 4 different groups, then there may be inversion of product. Means if the starting compound is S configuration, the product will be R configuration. If the starting compound is R configuration, the final product will be S configuration. RS nomenclature. This is the meaning of inversion of configuration or inverted product formation. So this is what is happening in presence of pyridine. So in presence of pyridine, we have free Cl minus, and this Cl minus is attacking the group alkyl group from rear side of the leaving group via SN2 mechanism, forming inverted product if R is chiral. But if reaction is taking place in absence of pyridine, in absence of pyridine, so what is happening is, let's see. In absence of pyridine, look at this, we have this R OS double bond O Cl. In absence of pyridine, there is no free Cl minus. आप कहेंगे सर यहाँ तो Cl था, लेकिन if you look at this HCl is a covalently bonded molecule gas. So covalently bonded molecule HCl does not have free Cl minus. In presence of pyridine, when this HCl gas is coming out from the solution, this is being trapped by pyridine to give you pyridinium chloride. So this Cl minus was attacking here. Now in absence of pyridine, there is no free Cl minus R, because this HCl being a covalently bonded molecule is kept from the reaction mixer, and there is no Cl minus. But we have to introduce Cl. So what is happening is, the Cl, which is a part of the leaving group, is attacking the reagent. So carbon from the same side of the leaving group, यहाँ पे लिखिए rear side से अटैक किया था, of carbon R and Cl, दोनों एक ही इंटरमीडिएट में प्रेजेंट है. तो दिस Cl जो अटैकिंग रिएजेंट है वो पार्ट ऑफ लिविंग ग्रुप है, तो इसका मतलब ये ऑपोजिट साइड तक को स्ट्रेच नहीं कर सकते. तो एक ही पॉसिबिलिटीज है, जिस साइड से ये लिविंग ग्रुप छोड़ के जा रहा होगा उसी साइड से अटैकिंग रिएजेंट भी अटैक करेंगे. तो दिस इज हैपनिंग हियर. तो ये इलेक्ट्रॉन इधर गए और ये इलेक्ट्रॉन्स लेके इधर से अटैक किया एंड दिस गिव्स यू RCl प्लस SO2। दिस मैकेनिज्म को हम लोग डिफाइन किया है एस NI सब्स्टिट्यूशन न्यूक्लियोफिलिक इंटरनल। Substitution nucleophilic internal. Why this is internal? Because the part of the living group decays from the living group and attach the carbon from the same side. तो अगर ये है, if these are अगर chiral है, then there is a retention of product. That means if the starting compound is S configuration, product will also be S. If the starting compound is R configuration, product will also be R. This is the reaction with thionyl chloride, that is SO2. We have this mechanism. This is the intermediate, and mechanism may be through in presence of pyridine or in absence of pyridine. In presence of pyridine, we have a reaction attack by PCl minus via SN2, possibility of inversion product. In absence of pyridine, the reaction is SNI, internal mechanism, because part of the living group Cl minus attacking the carbon from the same side of the living group, and there is a retention of configuration. So this is reaction with SOCl2. Now we will go to some other methods. Second method, that is direct halogenation of alkanes. Direct halogenation of alkanes. So we have this alkane. These alkanes react with halogen in presence of sunlight, when this gives you a mixture of haloalkanes. So a reaction is carried out in presence of sunlight. So we have to, some important things that we have to keep in mind. A reaction is free radical mechanism. The reaction process via formation of free radical. Next, the reactivity order of halogen X2. Fluorine is the most reactive, followed by chlorine, followed by bromine, followed by iodine. The reaction with fluorine is explosive, means highly exothermic, means it's very difficult to control reaction at room temperature condition, at room laboratory condition. Reaction with I2 is very slow and reversible. So we'll mainly focus on this Cl2 and Br2. For this fluorination and iodination, some modified methods will be used. Reactivity order of hydrogen, because hydrogen is being replaced by halogen. So we have different types of hydrogen: primary, secondary, tertiary. And the reactivity of hydrogen is tertiary hydrogen is most reactive, followed by secondary, followed by primary, followed by methyl hydrogen. So this is the reactivity order of halogen and hydrogen for this reaction. Now, as I told you, in this reaction there is a mixture of alkyl halide that is formed. With fluorination, reaction occurs in dark or absence of light. Even in absence of light, reaction may occur. But for this fluorination, bromination, iodination, presence of sunlight or light is compulsory for this reaction to take place. So take this. We have CH4. This reacts with chlorine in presence of sunlight. When this gives you CH3Cl, CH2Cl2, CHCl3, CCl4. All possible haloalkanes will be formed plus H6. Now we'll discuss some modified methods for iodination and fluorination. Modification for fluorination means alkyl fluoride. This method is known as halogen exchange method. Halogen exchange method. So we are starting with this Rx. This may be chlorine or bromine. Here X is Cl or bromine. Now this is meant to react with sodium iodide in presence of acetone. So sodium iodide dissolved in acetone reacts with RCl or RBI when this X is replaced by, this is for fluorination. This is made to react with reagents like AgF or HbF3 or AsF3. The reaction of alkyl chloride, alkyl bromide and alkyl iodide with AgF or HbF3 or AsF3 when this X is replaced by fluorine. This is what we call an exchange reaction. Means to avoid this explosion, we can carry out this halogen exchange method. This reaction is known as Schwarz reaction. So by this Schwarz reaction, we prepare alkyl fluorides, not by direct halogenation, because direct halogenation is very explosive in nature, highly exothermic. So to avoid this, we carried out this halogen exchange method, that is Schwarz reaction. Now modification for iodination. For iodination, we have two modified methods. First, by using oxidizing agent. Like HiO3 or HNO3, which is a very good oxidizing agent. So look at this. As I told you, RH plus I2, the reaction is slow and reversible when this gives Ri plus Hi. Now if you look at this reaction, Hi, this is a powerful reducing agent. And the reaction is in equilibrium. Now if we can destroy this equilibrium and we can shift the reaction in forward direction, then the quantity of Ri will increase. So we have to use Lee-Chatellier's principle. So means we have to disturb this. So to disturb this, we can remove this Hi. So Hi being a reducing agent, if this can be removed from the reaction by use of an oxidizing agent, so product removal, equilibrium is shifted in forward direction, reaction is moving in forward direction, the quantity of Ri will be increased. So this is the reason of oxidizing agent, is to destroy or remove the reducing agent Hi from the equilibrium mixture. So look at this. This reacts with HiO3 when this gives you I2 plus H2. So look at this. We are removing Hi from the equilibrium. Reaction is shifted in forward direction. Plus I2 is formed. I2 is the reactant here. So increasing the concentration of reactant, again reaction is shifting in forward direction. So this serves as two purposes. We are destroying product, reaction forward shift. Simultaneously we are increasing the concentration of reactant, again the reaction is forward shift. If this reacts with nitric acid HNO3, then also this gives you NO2 plus I2 plus H2O. So again look at this. We are removing Hi, forward shift, plus we also increasing the concentration of I2, again reaction is in forward direction. So whenever we carry out iodination of alkane, we always use some oxidizing agent so that the reducing agent Hi is removed and the equilibrium is shifted in forward direction and the quantity of alkyl iodide is increased. The second method for this iodination is halogen exchange. Halogen exchange. We have this Rx and this X may be Cl or this may be bromine. Now we have to replace this with iodine and the reagent uses sodium iodide dissolved in acetone. So acetone is solvent, this is the reagent, this is the reactant. So look at this, X is replaced by I and this gives you Ri plus NaX. Why we use specific sodium iodide? The reason being, out of the 4 halides of sodium, only sodium iodide is soluble in acetone and this gives you free I minus and free I minus attacks carbon and this helps in removal of X minus. X minus combines with Na plus to give you NaX, fluoride, chloride and bromide. This is insoluble in acetone, so there is no chances for reversibility of the reaction. This halogen exchange reaction for preparation of alkyl iodide is known as Finkelstein reaction. Finkelstein reaction. So this is direct halogenation of alkanes to give you alkyl halides. So for this we have modified for fluoridation and iodination. Now let's go for next method, that is from alkenes and alkynes. From alkenes and alkynes, that is addition of HX or Cl2. Under this we have first addition of HX, hydrogen halide. React with HX when this gives you, so this is alkyl halide. This reaction is electrophilic addition reaction and the electrophile uses H plus ion. This is coming from HX. Second, this reaction crosses through carbocation intermediate, formation. So as I can tell you, whenever there is a formation of carbocation, there is chances for rearranged product formation. Then this reaction follows Markovnikov's rule, that is formation of more stable carbocation means negative part goes to that carbon atom having more carbon atom, and the positive part of the reagent goes to that carbon atom having less number of carbon atom. That is Markovnikov's rule. The addition of HBr in presence of peroxide, that is anti-Markovnikov's rule, and the reaction is free radical. So because of this change in mechanism, the product is anti-Markovnikov's addition. So this anti-Markovnikov's is only with HBr in presence of peroxide, but if HBr in absence of peroxide, then that is Markovnikov's carbocation intermediate. So if you look at this mechanism, if this reacts with H plus sign, so H plus sign is coming from HX, so carbon double bond, this is nucleophile, this reacts with electrophile. Look at this, pi electron is shifted, carbon is negative, and this negative reacts with positive hydrogen, so this gives you cation here. And in the second step, this cation react with X minus sign to give you X. So this is addition product. Now these carbocation, as I told you earlier, these may undergo rearrangement to give you a more stable carbocation followed by reaction with X minus sign. Example is CH2 double bond, CH2 reacts with HI, again look at this, one more thing. Reactivity order of HX, HI, HBr, HCl, HF, acidic strength order. This gives you CH3, CH2I, CH3, CH double bond, CH2 with HI. Now look at this, Markovnikov's rule. Positive part, more hydrogen, negative part, less hydrogen. CH3, CH, CH3, that is Markovnikov's addition. Same, look at this, take this HBr, CH3, CH, Br, CH3, that is again Markovnikov's addition. But if the reaction is carried out in presence of peroxide, same, I react this HBr in presence of hydrogen peroxide. To HBr peroxide, reaction is anti-Markovnikov's addition, so HCH3, CH2, CH2, Br, anti-Markovnikov's addition product. So we have to keep in mind. So Markovnikov's addition, anti-Markovnikov's addition. That is addition of HX to alkenes. In the same way, we can also carry out addition of HX to alkyles. Same method will be followed. The only thing is 2 moles of HX will be added. So let me rub this. C, triple bond C, reacts with HX. So first look at this, addition of HX. Then this further reacts with second molecule of HX. So this will follow Markovnikov's in absence of peroxide, anti-Markovnikov HBr in presence of peroxide. So this gives you C, H, H, C, X, X. So this is giving geminal compound. Take this CH triple bond, CH reacts with HBr So this gives you CH2 double bond CHBr. This is with second molecule of HBr, CH3 CHBr2. So this is how product formation takes place. So this is addition of HH double bonds and triple bonds. The second method, that is addition of its reaction with H2 halogen with H2. This gives you dihalides, that is vicinal. Similarly, we can take this alkynes reacts with halogen. Only difference is 2 moles will react. Simply this is addition reaction. Tetrahalides will be formed. So both this alkene and alkyne can be converted into polyhalogen substrate alkanes by addition reaction with X2. This is polyhalogen substituted alkanes. Simply HH addition gives you alkyl halide or di-substituted alkyl halides. This is from alkenes and alkynes. The third method is substitution reaction. So we have looked at this CH2 double bond CH3, that is allyl group. This reacts with halogen in presence of sunlight or high temperature. This may be chlorine or this may be bromine. When this gives you allyl substituted halogens. So keep in mind, in presence of sunlight or at high temperature means heating. These types of reaction goes substitution reaction at allylic position. So this is known as allylic substitution reaction. Here the reaction is proceeding through free radical mechanism. So keep in mind this reaction condition. So take this example. CH3 CH double bond CH2 reacts with chlorine at high temperature. So this gives you CH2Cl CH double bond CH2, chlorination, allylic chlorination. Now for bromination we can carry it out in this way. Bromine, high temperature, CH2Br CH double bond, or we can also take a look at this. Bromine in presence of NBS, N-bromosuccinamide. This is a specific reagent used for allylic bromination. NBS, CH2Br CH double bond and bromosuccinamide. Okay, specific reagent for allylic bromination. SO2CO2, sulfuryl chloride, is specific reagent used for allylic chlorination. CH2Cl CH double bond. So to get this, simply addition of halogen gives you addition reaction, but if halogen is reacted with this allyl group in presence of sunlight or high temperature, this gives you allylic substitution reaction, that is from alkenes and alkynes. So this is preparation from alkenes and alkynes, and take this reaction also. So we have looked at this. So this is allylic carbon, So react with this chlorine in presence of sunlight. So substitution takes place at this allylic position. CH, Cl, CH3. This is allylic position. Look at this. CH3, sp2, sp2. This is allylic position. So again, substitution takes place at allylic position. Next method, that is from silver salt of carboxylic acid. From silver salt of carboxylic acids. From silver salt of carboxylic acids. So we have this RCOOAG. This is the starting compound, silver salt of carboxylic acid. This reacts with H2 when this gives you RX plus AgX plus CO2. This reaction, now look at this, maximum yield. Now X2 can be, this can be I2, this can be Br2, this can be Cl2, but Br2 gives you maximum yield. The reason is OBr bond is weak and AgBr is least soluble, and R should be primary. So maximum we carried out this reaction for alkyl bromide preparation, and this reaction proceeds through free radical mechanism. The reaction is free radical mechanism, maximum yield with bromine because OBr1 is weak, AgBr is least soluble, and alkyl should be primary, and this reaction is known as Borodine-Hunsdiker reaction, or simply say Hunsdiker reaction. So as I told you, this is specific used for preparation of bromide. So look at this, RCOOAG reacts with bromine when this gives you RBr, AgBr, and carbon dioxide gas is released. So look at this mechanism. So we have this RC double bond O, O minus Ag plus silver salt. This reacts with Br2 when this gives you RC double bond OOBr. So this bond is a very weak bond, and AgBr is precipitate. In the second step of this reaction, RC double bond O Br. So we have a pair of electrons. So these undergoes homolytic cleavage, resulting in the formation of free radical. RC double bond O, O radical, and Br radical is formed. So Br radical further reacts. This being unstable, immediately decompose to give you carbon free radical and carbon dioxide. So these decompose to give you carbon radical here. This electron is transferred here. One electron is transferred from RC bond, and this gives you R. So E R radical plus CO2. In the third step of this reaction, These are radical. Again react with this R C O O Br. From this Br is taken up, giving RBr plus RC double bond O radical is formed. This reaction is recycled here. So this gives on as chain reaction. So this is how this alkyl halide is prepared from silver salt of carboxylic acid. So this reaction मैंने आपको कहा था कि maximum yield is given for RBr. For this R should be primary. The reason is OBr bond is a weak bond and AgBr is a least soluble, so this can be easily precipitated out. So this is from silver salt of carboxylic acids. So look at this. These are some of the general methods of preparation of alkyl halides from different compounds. So keep in mind the name reaction that I have mentioned. So with this we come to the conclusion of preparation of alkyl halides. In the next we'll take up properties of alkyl halides. Bye bye.